Okay, so we're looking at question 7 from the D1 January 2012 mock. A lot to it, actually, isn't there? Let's have a look at it. So it's all about traveling salesperson, isn't it? So complete table 1. Okay, so we're looking at incomplete graph here. So basically, part A for 2 marks is just asking us to make it complete, if you like. So let's have a little scroll down. Let's have a quick heads up on what's going on. So okay, so A to E. Oh, I see what's going on. To get from A to E, the shortest distance is going to be, it looks to me like you're going to travel down here and then down here. It's A to E. So it's like you're imagining it's like, yeah, let's say there's an edge there worth 8. That's all that's going on here. And it's to do traveling salesperson analysis, you do need a complete graph, yeah. So that's what we're sort of mimicking here. So let me blast on this table, and you can check it at your leisure. It's going to be 8, 7, 13, 4, 10, and 19. So the same numbers going here. 8, 7, 13, 4, 10, and 19. So now we're away. So part B. On the completed table, use the nearest neighbour algorithm starting from B to find an upper bound for the length of Sam's store. All right, can handle that. I'm not going to actually draw anything on my table. I only sort of do stuff to the table when we're talking about prims on the table or the lower bound algorithm. So you just do it by inspection. I think 4 marks is a piece of cake, isn't it? So if we're at B, the nearest vertex to B, I scan along. Let me get the highlighter pen out. I scan along this list here, or down, I suppose. But I'm going to go across. I'm going to get rid of that in a sec. It's obviously 2, isn't it? So I go to A next. The nearest neighbour to B is A. And what I'm going to do, I'm going to keep a track of the numbers as well. So that's 2. Okay, I'm now looking from A. The nearest neighbour to A is D, and I've travelled 4. I'm at D. I want to go to a vertex that I haven't currently been to. The nearest is going to be E. So D to E, we can see from the table, is going to be 4. From E, the nearest neighbour that we haven't been to so far is it's F, isn't it? Is it F at 10? I think it is, yeah. The nearest neighbour to F is going to be G. And F to G is the nearest, isn't it? It is a big number, but it is 20. Okay. From G, you're going to go to. Let's have a look. Hang on. I'm getting a little bit lost here. The only vertex left, we've got to go to C, haven't we? We're forced to go to C. So from G, we're going to C. That's 32. And of course, some people forget this, which is crazy. You've got to complete the Hamiltonian cycle. You've got to go back to B. So C back to B. Because we've been to every vertex exactly once, but we want to start and finish at the same vertex. B to C is 6. So now what I need to do, so I've listed the route. I need to add these numbers together to get my upper bound. So when I add this number, what do I get? 6, 10, 20, 40, 80. So the answer to B part 1 is 80, and that BADEFGCB is the Tor. Tor is another word for Hamiltonian cycle, of course. Okay. Where does the question go next? Write down Sam's actual route if we were to follow the Tor corresponding to the answer in B part 1. Okay. It's because the graph isn't complete. So let's I'm going to be scrolling up and down here, folks. Sorry about this. I just couldn't make it all fit on the same page. So B part 2. So it's going to go B to A. That's direct, isn't it? B to A to D is direct. This starts off well. So it goes B to A to D. Do you know what I'm going to do? I'm going to draw this one in red up here. She's gone from B to A to D. Okay. And then it's got to go to E, F. Oh, we can get to there. This is going swimmingly, so you can go down there. E to F. So it's as before so far. B, A, D, E, F. From F, it's got to go to G. Oh, this is going swimmingly well. Got to go to G. And then he's got to go to C. Aha, this is where it takes a slight turn for the worse. Not disastrous though, is it? To get to C, let me show you. We're mimicking this edge here, yeah? It doesn't exist in the actual network. To get to C, let me get rid of that. To get to C, he's got to go up to E and then down to C. Let's put that in here then. So we'll go to E and then C. And then You want to get back to B. Can you get back to B directly from C? Nah, you've got to go you've got to go to A, back to B. A, back to B, back to B. Come on. What is going on? Back to phew, B. And that's it. Yeah, not too bad. Right, so B part 3. Starting from each of the other vertices in turn, 77, 70. Basically, when it comes to, because these are all upper bounds, you want the smallest upper bound, yeah, because that actually exists as a tool. You can actually, use that in real life. So the smallest number for B part 3 is, the smallest number out of those is 76. And that concludes, does it conclude? No, it doesn't conclude the question. There's more. Right, I've got it on the next slide. Here we go. Right, 7C part 1, flipping it. So we've been dealing with upper bounds. It looks like we're going to be finding some lower bounds now. On table 2 below, okay. That's all right. We're just going to do prims on the table. So let's have a go at that then. When I do prims on the table, and I suggest you do exactly the same, I draw out the graph as I go. I get a visual on what's happening. I think that's important. Yeah, we're after a minimum spanning tree when we're using prims. So starting from A. So we're at A, so I'm going to draw it and use the table at the same time. This is when I do sort of put marks on my table. Okay, so we cross that out, we don't need to go back there. Okay, the nearest vertex to A is B, distance 2. So we went to B second, and we can now cross out that there because we do not need to go back to B either. We now look down both this column and this column, and we look for the smallest number. And it seems the smallest number is going to be, I should also say, folks, sorry, I'm just going to backtrack here. This is part of your working. What I should have done, and I apologise that I'm doing this after, I should have circled that number there. Okay, so I look down column 1 and column 2, and I notice that 3, so I circle it, is the smallest number. So from B, I add D, and the distance is 3. So I added D as my third vertex. I cross out D, don't need to go back there because it's now added. Now I look down these 3 columns for the smallest number. Okay, can I do better than 6? No. So I add C from A. So from A, I add C, and it is distance 6. So I circle it. I've added C fourth, and I cross it out because I don't need to go back there. So I'm now looking down these 4 columns. Okay. The smallest number is, can I do better than 16? Yes, I can do 15. 12. So from D, I add F. So I added F fifth. From D, I added F, distance 12. And what I do now is cross that out. I don't need to go back. Okay. So I'm now looking down these 5 columns here. I need to add vertex G. I'm going to add G from F at distance 20. So I added G sixth, and I've now got the whole. Here it is in pictorial form. That's my minimum spanning tree. So the question is, it asking me, so hence find a lower bound. Okay. So the minimum spanning tree, this is going to be 7 marks in total for the lower bound. So therefore, minimum spanning tree is, I need to add those numbers together. 6 plus 2 plus 3 plus 12 plus 20 gives me, what does that give me? Does that give me 8, 11? I think it's 43. Yeah, 43. Okay. So that's what I've answered there, just so we're crystal clear. That's all of C part 1. And it says, hence, find a lower bound. Okay. Now, they've led us by the hand a little bit here. So we're talking C part 2 here. C part 2. Okay. Just going to skip back here. Do you notice how, what they've done, they've deleted this vertex, yeah? So they've removed E4. So what we need to do, I'm going to skip back to the next slide in a sec. We need the 2 shortest back. Now, the 2 shortest back, 4's the shortest, and 7 is the next shortest. So for our lower bound, so let's skip forward one. This is simple now. So for this, it's going to be 43 plus 4 plus 7, i.e. the 2 shortest back from the previous page. So therefore, our lower bound is equal to, if we add those numbers together, we get 54. And that's 3 marks. Not too bad at all. Okay, scrolling back up. So this time, these are all the lower bounds here. Because these might not exist, you want to write down the best lower bound. The best lower bound is the largest number. So the answer to C part 3 is simply 64. And part D, I'll answer it in green up here. Given that the length of a minimum tour is 2 miles, use your answers to B and C. This is alright. So I know that 64 is my lower bound. So 64 is going to be less than or equal to T. And I've forgotten already, folks. I've got bad memory here. It was, of course, 76. So that's less than or equal to 76. And you've got to write it in terms of mathematical symbols, yeah. Use the inequality signs, yeah. We're mathematicians after all. And that's a question. That was a long question, folks.